Hello everybody, today I want to introduce you to TensorBank, our Tensor Lakehouse implementation. And before we start, I just want to introduce the, let's say, state-of-the-art architecture for a tabular lakehouse. So just maybe one word about the term lakehouse. It's basically composed of a data lake and a data warehouse. So you have the data lake properties with nearly unlimited and very cheap storage, mostly nowadays by S3 or Cloud Object Store. In the early days, it was cheap HDFS storage from the Hadoop ecosystem. Yeah, and then you have the data warehouse, which actually allows you to write SQL queries against your data. And if you just merge those two things, you will get a lakehouse. And I'm saying here tabular lakehouse because we also are kind of coining the term Tensor Lakehouse. More on that later. But what you see here for tabular data, where you can basically query data using SQL. One of the two emerging standards are Presto or Impala, and most of the folks are currently going with Presto. This is the query engine, and then you have table storage format. The idea is you can store tables in files like Parquet or Avro, but at that moment you are losing the whole integrity properties, because while you are writing files, they can be part of the result of a parallel query, and that might give you inconsistent results. So what Iceberg, Hoodie, and Delta Lake do, among some other things, is they manage actually different versions of tables. So a table is composed of, for example, a set of Parquet files, but internally metadata is kept, and while, for example, data is added, so new Parquet files are written, a new version is created, but all the queries are still running against the previous version. So only once the whole set of files has been written, a new version has been created, then the query will run against, or all the queries will run against the new version. And as you can see, is S3 or Cloud Object Store is supported in that scenario. That means you have this property of scalable and super cheap storage, which everybody likes. So we brought this to a more generic scenario. Generic in the sense that we support arbitrary tensor sizes, not only tabular data. And on the other hand, our implementation is here on the left-hand side specific to Earth observation data, but the rest of the stack is basically generic. So we can also use this stack, for example, for fMRI data or DNA sequence data and so on. But in our case, we are using it for Earth observation data, so satellite images, and also for climate data. So you might have heard about xarray. If not, xarray is a library which basically merges the properties of pandas data frames and NumPy arrays. So you can think of xarrays as some sort of a high-dimensional pandas data frame. So it's not only used for tabular data, but also for multiple dimensions. No, for example, in satellite data, you have, for example, the longitude and latitude. So that's 2 dimensions. Then you have time. That's 3 dimensions. And then you have different spectral bands, for example. Then you have a dimension per spectral band, and so the dimensions easily blow up. For parallel computing, we can use dask. So there's an integration between xarray and dask. And whenever you compute something on xarray, then xarray can make use of dask and basically use a dask array in the background and execute that in parallel on multiple nodes. How to create such a xarray is basically straightforward. You can lazy load files in the, as I said before, in the tabular case, it's Avro or Parquet standard. And for high dimensional data, there are 2 other standards. One is zarr, which is basically a compressed array data structure, and it supports high-dimensional data. And also the good thing about zarr and coq is it supports the metadata to be stored right at the beginning. That means if you want to know what's inside the file, you only need to read the metadata first, and then you can compute all the offsets and then access subsequent blocks. And that's very handy. The same holds for coq. Coq stands for Cloud Optimized GeoTIFF. So it's an extension to the TIFF image format, and which has geospatial metadata. And then the cloud optimized version of it, it has also in the metadata section all the offsets you need to extract subtensors from that file. So it doesn't matter which of those two you use. We use at the moment coq for satellite images and zarr for climate data. And that's all residing in Cloud Object Store. So that's a relatively straightforward stack. So this whole stack between xarray and S3, that's also known under the Pangeo name. And now what we do is we add another layer on top. This is openeo. It's an open standard, and it actually is a data cube API. The cool thing is you can have thousands and thousands of files in petabyte scale S3 buckets, but you still can query the whole thing as it would be one super large hyperdimensional cube, and you can slice and dice through that cube. So for example, you can subset by location or by band, so by modality basically, or by time intervals, and then you can extract subtensors. That's fine as long as you don't need to know what's inside the tensor. And for that special case, we have here created the hierarchical statistical indices, HSI, where we pre-compute a certain amount of statistics at different resolution levels first, and then we can use those data either for directly answer parts of the query or the whole query, or we can just during execution decide whether it's worth to read the subtensor or not from the large hypercube. So in order to understand this a little better, let's consider this square on the left-hand side. So on the left-hand side, these are just data points from A to BL. And what we then do is at a certain resolution level. So let's consider this is resolution level number 1, where you bin 16 data points into one statistical field. And then over those data points, you compute different statistics. For example, here the mean, minimum, maximum, standard deviation, some quantiles, median, and also in a use case specific fashion, we can say what's the probability that in that image, for example, clouds are present, or ocean, or land, or whatever. And of course, like bring your own statistics. Now, whatever you want to compute, you can add to that index. Whenever you add data, then the index is also computed and also at different resolution levels. And you can then drill down this index, for example, until you find a region which doesn't have clouds. Okay. So this is basically the architecture. Of the whole stack. So we support any type of file system. So we can use local file systems, cluster file systems, or Cloud Object Store. I mean, if you are able to use Cloud Object Store, you can also use any type of POSIX compliant file system. No, they are much more powerful than Object Store. The only reason why people are using Object Store is because of the low cost. So I have to say we can support file systems, but in addition, we also support the more limited Cloud Object Store S3 API. No? That's what I want to say with that. Yeah, you see here the HSIs are sitting here. We store them at the moment in GeoParquet files, also on the storage here. And then we have here the COG and zarr format. As a side note, we can also support key value stores like Apache hbase, but this is not very important in this moment. And then the other thing is, in order to make this magic happen, know that you have a unique view on your whole data set, you need to index your files, and we are using here something which is called stack, spatial temporal asset catalog. And this guy here actually indexes all the files with the metadata, and that way, and then the data is stored in PostGIS, and you can then query against this catalog. That's actually what openeo is doing. Openeo is querying against this catalog here and finds out what files it needs to read. And then it can consider a file. So if openeo finds out it has to read a file, it can just read the metadata via HTTP range reads. That's why it's advantage. There's an advantage if you have the metadata at the beginning of the file, like it's in the case for zarr and COG. That way, openeo can just read the first block of those files and find out what subsequent blocks can be skipped. Then we have two other interesting things. One is the federation core. So since openeo, when you obtain a data cube and you apply functions on the data cube, this is all translated into an openeo execution graph, and that graph can be actually split. So we can have an overall cross data center execution graph, and then we do some smart splits, and then we send the subgraphs to the data centers, which also have an openeo API. And then we obtain sub results from those, and that's a way to minimize data transfer cost and the data gravity problem. No? And the other thing what we can do is, besides answering queries or optimizing queries via this hierarchical statistical indices, we can also use them for de-biased sampling. So let me actually show you what I mean by that. So, okay. So what we have is actually a way to provide torch datasets, and those are making use of the HSI. And let's consider this example here. So we have data points from all over the planet. And if you sample randomly, then you will get a majority of your samples from water containing regions, so the ocean. No? And you see here are different categories. And I think 152, that's water. You see in most of the cases you will get back water. And that's not super interesting for a deep learning model to be trained on. So what we want to do is we want to de-bias. And what we can now do is, since we have the statistics and the contents of the original images in the index in different resolution levels, we can easily just query that index first and find out if it makes sense to further drill down the index and see whether we find something interesting. Now, in this case, we provide here a distribution of data we want to have. No, this category 1 to 1. I think 1 to 1 is a highly populated region. I think 1 to 1, 1 to 2, and 1 to 3. So we want to have an emphasis on those categories. So that's what we specify. So that's the de-biased sampling we request. And then what we here did in experiment, this is an experiment which was continuously running and updating this histogram. We got back this distribution here. And if you compare that to the original distribution, you see it's clearly de-biased now and is more and more reflecting the actual histogram which we specified for the distribution of data. Okay, so this concludes my talk here, and I hope you found it interesting. And if you have questions, you can put them down in the comments and also in the question section. Thank you. Bye.